Hello, we're going to talk about topic 6.4, the fundamental theorem of calculus and accumulation functions, right? So last lesson in 6.3, we talked about how the integral or the definite integral finds the area under the curve with an infinite number of subintervals. So what we're going to do is we want to talk about kind of some properties or some relationships between this integral and the derivative. All right. So let us say, so I have a little blurb here. We know that the interval starts at a, but we don't know where it stops, right? That means the interval is going to go from a to x, where a is a constant and x is an unknown variable. We can represent that function to be a little something like this. So I'm going to start with saying the integral that goes from a to x of a lowercase f. Now I don't want to use an x again because I already used an x dt, right? So whatever letter I use inside the function is the same letter that I'm going to use for the width of those rectangles, right? So this would be my function for capital F of x. Now we are going to give that capital F of x a name here in a little bit as well. So that's why I used a capital instead of a lowercase. So for number one, right, if I say that capital F of x is the integral from 0 to x of f of t dt, and I give you a graph, right, use the table of values to estimate or to determine the area under the curve from 0 to 5. So if I were to let x be 0, right, and I'm going to write right underneath this, if I were to let x be 0, I'm going to get the integral from 0 to 0 of f of t dt. Now, if I do the area from 0 to 0, well, that rectangle doesn't have any width, so it's not going to have any area, okay? Now, if I were to do the same thing, let's say I do the integral from 0 to 1 of f of t dt. So now I want the area from 0 to 1, and I get a nice looking trapezoid here. So if I were to do 1/2 the base 1 plus base 2, right? So 3 plus 2 is 5 divided by 2 is 2.5 times height. So this would be a 2.5, right? If we found the area of that trapezoid, you should get 2.5. And we're just going to keep going. So now I want the area from 0 to 2. Notice I just keep changing the x value. So of f of t dt. So the area from 0 to 2 will now be this whole section. Again, I have another trapezoid. So 3 plus 1 is 4 divided by 2 is 2 times the width of it, which is 2. So I'm going to get an area of 4. And keep going. I have the integral from 0 to 3. So we're going to add another box to it. Well, if I add another box to it, this is just going to become 5. I just added that little square. If I add this little triangle to go to 4, right, this is going to be 5.5. And then down here, if I subtract this little triangle, then I'm back to 5, right? So I get this table of values. And you can even, if you wanted to, you could plot that table of values, right? I could say, okay, I started at 0. We don't always start at 0, by the way, but in this case we did. At 1, we're at 2.5. At 2, we're at 4. At 3, we're at 5. At 4, we're at 5.5. And at 5, we're at 5, right? So I get something that looks fairly quadratic. We cannot say that it's quadratic. We don't know what happens between those values. We can't really connect those dots, but we can kind of get a picture of what it looks like. Now, this is what we call an accumulation function. Okay? It's an accumulation function because as I went to different x values, we just accumulated more and more area. All right? So the fundamental theorem of calculus that we're going to discuss, and we're going to focus on part 2. There is a part 1 here, but we're going to focus on part 2. If you were to take the derivative of an integral from a to x, what we end up getting is just lowercase f of x. Okay, so it's kind of like I'm taking this x and I'm substituting it in. Now, there is a little bit more going on here, all right? But derivatives and integrals, if I were to take the derivative of an integral, they cancel each other out. They are inverses of one another. Okay, so if I take the derivative of an integral, they are inverses of one another. They cancel out. All right. And if we have a derivative, capital F of x is what we call the antiderivative. Fancy word. Okay. Anti just mean an opposite, right? So it's the opposite of the derivative or inverse of the derivative. Variations. Now there are some variations. Okay, and I'll get into this probably in class. I'll pair this with the idea of how this relates to the fundamental theorem of calculus for part 1. But just to keep the video short here, if you were to do the derivative of this problem, what we're going to do is we're going to still substitute this in, okay, which would give me an f of g of x. But we would have to multiply by the derivative of the inside. Okay, so anytime we have an expression of x up there that's not just x, it's got other operations involved with it, we are going to still substitute it into the function, but we're going to multiply by the derivative of the inside. Now, when we have an expression on top and bottom, we have to do two things here. We are going to start by substituting in the top piece times the derivative of the top. But then we're going to subtract the bottom piece, and we're going to do the same thing. So we're going to substitute in the bottom piece times the derivative of the bottom, right? So that's kind of how it works. So we'll plug in the top, always the top first, times the derivative of the top. Then plug in the bottom times the derivative of the bottom and subtract those two, right? So let's do a couple examples. So we'll start off with just the basic idea here. So if I were to take, and again, the directions want me to find f prime. So I want the derivative of the integral from 2 to x of 3t squared plus 4t dt. So if I do this, this is going to give me a 3x squared plus 4x. And this would be my answer. Again, I just substituted in the x to the function, and I had two places to substitute it. Okay, so let's do it again. Same idea. So I want f prime, so d over dx is going of pi over 2 x cubed of sine of t dt, right? So when I have this, now I have an expression on the top, right? So I'm going to take that expression and I'm going to substitute it in for t. So I'm just going to get sine of x cubed, but I need to multiply it by the derivative of that expression. Now, if you might notice on the last problem, I didn't multiply by the derivative. The reason being is because the derivative of x is just 1, so you don't really see it, so it doesn't really make too big of a difference. All right, so if I keep going, same idea, d over dx of the integral from 1 to 4x of h of t dt. I am going to get h of 4x times 4. And we don't know what h is, so this is the best that we can do. Okay. Now let's do a couple problems where we have expressions on the top and bottom. So if I were to do this, I'm going to say d over dx times integral from a negative x to x of 5t dt. And that's going to give me a 5x times 1. Whoop, that came out messy. Hang on. Times, right, the derivative of x, which is just 1, minus 5 times a negative x times the derivative of negative x, which is a negative 1. Got a lot of negatives going on there. So that's going to end up giving me a negative 5x, which will give me 0 in this particular case. Okay? How about we do one more, just to practice. D over dx of the integral from 2x to 3x of t squared minus t dt. So if I plug in the upper limit, I'm going to have a 3x squared minus 3x times 3 minus a 2x squared minus 2x times 2, right? And if we wanted to, we could simplify this. This would be 9x squared minus 3x times 3 minus a 4x squared minus 2x. Oop, didn't need another parenthesis there. Times 2. And so that gives me 27x squared minus 9x. Now be careful with your negatives here. This is going to be a minus 8x squared plus 4x. So that gives me a 19x squared minus 5x to be my answer. Okay? And you can see there's just more of the same, right? There's tons and tons, right? So what I'll do is I'll try to post an answer key for this so that way you can check to see if you're doing it right or wrong. But again, the idea here is the most basic one is if it's just an x on the top, we just plug that in. The derivative of an integral just gives us f of x. If we have an expression of x, then we have to make sure we multiply by the derivative of that expression. And if we have an expression on top and bottom, then we have to do the same thing twice and subtract those two. Okay? Hopefully this helped, and I'll post the answer key for you to check your answers on the practice.